My name is Zhang, and I'm currently a postdoc researcher at UC Berkeley. And I got my PhD at CMU under Professor Eric Xin. And my research is about large-scale algorithms and systems for machine learning and AI, especially on the training. And welcome to Castle Workshop, and welcome to my talk. And so in this talk, I will cover two parts. So first, based on what Hector already presented, I will go a little bit deeper to talk about to use 10 minutes to introduce some background and history about the large-scale deep learning systems development in the past 10 years. And in the second part, I will also dive a little bit deeper to the system Alpa, which was used to support the demo you just see. Yeah. And before I dive into the details, I want to first share two links. So the first link, alpa.ai, is our project page, so feel free to check it out. And the second link, opt.alpa.ai, is a free online service that you might be interested in. And it provides a free and limited GPT-3-like text generation service powered by Alpa. And this service is actually hosted here at MBZUAI. And as far as we know, this is the first free GPT-3 text generation service in public in the world. And please visit this link and give it a try. Yeah, cool. So let us begin with the first part. And I want to use the first part to give you an overview of the distributed machine learning system development in the past 10 years. So I want to begin with one of the most prominent research agenda in machine learning community today, large models. And probably as everyone has heard many times today, a lot of recent advances in deep learning are enabled by big models. So since 2018, the largest model size started to increase more than 10 times every year. And 2 years ago, OpenAI released the very famous GPT-3 model with 175 billion parameters. And this model is recognized as one of the most important breakthroughs in machine learning. Today, the benefit of scaling machine learning model does not diminish. People are still trying to train larger and larger models. And meanwhile, large models are also made more and more accessible to the general public. Like 4 months ago, Meta open sourced this pre-trained language model called OPT, 175 billion parameters, and making large language model at this size first time available. And about 2 months ago, the Big Science Initiative open sourced another language model called Bloom. And it has like 176 billion parameters. Yeah. So as a machine learning developer, how can we embrace large models? Well, large models can provide a lot of benefits. It also poses a lot of new challenges in computing. So to see the core challenge, let me use a very simple example. So many of today's machine learning programs often assume the model, such as this bird, can fit into the memory of a single computing device, like a GPU or TPU, right? And with this assumption, all the computation is conducted on a single device using framework like a TensorFlow or PyTorch without any problem. However, when the model becomes large, it's hard to fit the model or even a single layer of this model into this limited device memory, which is usually 16 gigabytes. And how can we train and serve these big models? This becomes a really hard problem. The only possible way is to partition and parallelize these big models on more devices. However, this partitioning and parallelization requires a big amount of engineering effort that is specific to the model definition and also the cluster you are going to use. So in this talk, I try to use this as the opening, and I'm trying to tell you from a system perspective what drives us here with these large models and systems, and what are the systems that are available for you to play with these large models in your production and research. Okay, let's start by first giving a brief overview of the history of distributed deep learning system in the past 10 years. What happened there? So let's start from 2012. So 2012 was really an amazing year, and I guess most people have saw this figure many times, right, since that year. This is AlexNet, and the very first GPU-trained convolutional neural network that has driven a lot of revolutions in machine learning. Well, AlexNet is indeed not a big model for today's GPUs, but it actually cannot fit into one GPU in 2012. And despite its record-breaking image classification performance, a key insight behind AlexNet is that they actually are parallelized over 2 GPUs. So in this network architecture diagram, we can see the convolutional kernels and the fully connected layers are splitted and executed on 2 parallel GPUs. So in the same year, neural rips, there was another highly influential paper by Google called Disbelief that trained a really large, fully connected neural network on a very, very large CPU cluster. This model actually has 1.7 billion parameters, which is still considered as large even today, right? This was made possible by partitioning and computing on 10,000s of CPU cores. So behind these 2 models, there are 2 specialized distributed machine learning systems that make their training possible. And these are the early reflections of how parallelism and systems plays a critical role in machine learning innovations. So since AlexNet, a lot of neural network architectures, especially CNNs, have been designed between 2012 and 2016. The top 3 include like GoogleNet, VGG, and ResNet. But the size of the model did not grow as fast as the memory of GPUs, thanks to NVIDIA, right? And hence, the majority of deep learning parallelization research is to use data parallelism to accelerate their training when there are more GPUs available. So this data parallelism support was initially provided by a system called parameter server. Actually, the inventors of parameter server are sitting here, Qirong and Eric. They laid the foundation. And shown this figure, which was designed for SGD-based distributed optimization. And as you can see, this architecture of parameter server closely corresponds to the parallel SGD algorithm, which is used to train neural networks. And the model computation, such as this forward and backward in neural networks, is replicated across multiple workers, but the parameters to be optimized are held centrally on the servers. And at every iteration, each worker sends its gradient, which is the lambda W, to the server once they are ready. And then the server aggregates the updates from all workers and applies the updates following the update equation, such as SGD. And then broadcast the new versions of parameters back to all workers, so they can start the next iteration computation. And we usually call this step synchronization. That's the key feature that the parameter server architecture tries to provide. So a unique advantage of parameter server architecture is that it actually has the flexibility to incorporate asynchrony into the data parallel updates. Instead of synchronizing the worker at every one training iteration, we can synchronize them every a few iterations. Hence, we can reduce the communication between worker and server in compromise of the consistency of the updates. So since the data parallel computation is intensive and the network bandwidth between nodes is rather limited, this makes parameter server a main theme of distributed machine learning research and also in production between 2012 and 2016. And the various versions of parameter servers and corresponding SGD algorithms have been developed by the machine learning community, aiming at reducing communication while still maintaining the same quality of machine learning convergence of your trained model. So in the deep learning regime, a lot of parameter server has been repurposed on top of some early frameworks to enable GPU-based parallel training, which I gave a few examples here. That's what happened between 2012 and 2016. So despite the many parameter server implementations, let me ask you a question. So how many of you are still training your model, like BERT and CovNet, using a parameter server? I guess very few, right? So I guess a wider adopted interface is the one shown in this code, PyTorch DDP. I think many of you have seen this many times, which uses or reduced to synchronize data parallel updates. This interface is also quite simpler. So the users append a single line interface DDP to wrap a model object, and the data parallel computation will automatically take place on parallel GPUs and workers and synchronize gradients at the end of this train step function. Yeah, and this makes parallel training very easy. And this in the backend, this is enabled by a very famous operation called OR-reduce. So, but why would people do so many research in parameter server, but ended up with just using a very simple operation called OR-reduce? The reasons, in my opinion, are twofold. So first, a majority of hardware setup for deep learning research resembles the topology shown in this figure. So where 4 or 8 GPUs are installed in one node. And this is actually a very standard architecture provided by NVIDIA, and a lot of companies and universities are purchasing this kind of architecture. And the data power training of neural networks rarely go beyond the one node in this period, like before 2016. And the communication between GPUs inside one node isn't actually a bottleneck due to the fast interconnect between GPUs, such as the PCIe and the NVLink. So most machine learning researchers have found the synchronous training sufficiently fast and may not want to use asynchronous training because it will compromise the convergence quality. And second, all-reduce happens to match with the communication pattern in data parallel distributed deep learning. So each rank in all-reduce, each rank, which is a worker or a GPU, generates its own copy of gradients, and all workers perform an all-reduce to get the aggregated gradients. So this pattern has been studied so well in high-performance computing community and by system researchers for more than 20 years before machine learning actually become prominent. So a variety of very fast all-reduce algorithms and libraries such as the MPI, NCCL is readily available for these types of communication. Yeah. So as a result, this has enabled the machine learning research to train on increasingly larger data set to get better machine learning results. Okay. Well, data parallelism has been made as simple as just adding a single line of code. Let me ask you another question. So how many of you have met the out-of-memory error immediately after you just launched your training job? So what was your fix? Reducing your batch size or model size, right? And how many of you have found a solution that does not compromise your batch size and model size? So in fact, there wasn't much you can do unless you're hacking into the low-level code and building some custom parts that you can code by yourself, like those done for the early old system like AlexNet and Disbelief. So this situation was significantly improved since the open source of TensorFlow. In TensorFlow, the model computation is formalized as a computational graph of operators and tensors. And while the cluster is expressed as a cluster of layman devices, for example, GPU1, GPU2, GPU3, like that. And the TensorFlow provides very high-level API to place an operator or tensor onto a device, like this one shows, where we are trying to place a few operations on a GPU called on a device called CPU0, right? And with this design, given the computational graph of a neural network, we can create a placement for each node of the graph and end up with a very complex model parallel strategy, as this figure shows, where each color corresponds to a placement of a node on a device. So this greatly eases the creation of big neural networks and facilitates the development of parallelization techniques for big models. But it also leaves a lot of open questions. For example, what is the most efficient parallel strategy for a model like GPT, right? And or for a cluster with a different number of GPUs and networking topology. Okay, so started from 2018, as I have mentioned, and as the hacker also mentioned, the model size, especially in natural language processing, increased several orders of magnitude per year. So from Elmo with 95 million parameters to T5 with 11 billion. And the sizes of this model greatly exceeds the memory of concurrent GPUs and cause for new model parallelism techniques. So naturally, depending on the model created, a set of model parallelism techniques have been developed in order to support the training or inference of such big models. And these slides give two notable examples. One is the Megatron LLM by NVIDIA, and the other is GPIF by Google, and which represent two classes of parallelization techniques for big models, which I will talk about later. So these model parallelism techniques, when combined together, enabled the creation of OpenAI's GPT-3 language model in 2020, which is often regarded as one of the most important machine learning models in this decade. And GPT-3 with 175 billion parameters demonstrated the great potential of big models. And it has also become a key driver for many new and machine learning and NLP results. So, and OpenAI and a few other startups even developed a business to charge users for using their GPT-3. So since GPT-3, a lot of big models have been trained, such as Google's Palm. And 4 months ago, Meta open sourced the OPD 175 billion, which I have mentioned. And so 2 months ago, this Bloom model. So from the computing aspect, how can we better embrace big models? That's a high-level question I try to answer in the second part of this talk. And cool. And that's a quick introduction of what was going on in deep learning parallelization in the past few years. And now we're ready to start the second part. So as I have shown that as models become bigger and bigger, the only possible way to still play with such models is to partition and parallelize big models. But as I also explained, this step is actually very, very difficult. So that comes Alpa. So Alpa is a system that we designed to specifically facilitate the training and serving of such big models. And hopefully after the second part of the talk, you could be convinced that Alpa can help you better embrace these big models in your research and development. So to introduce Alpa, let us begin with the computational pattern of deep learning. So first, we have a batch of input images, and we feed the input into deep learning model. And the computation involves a forward propagation to compute the prediction, and then a backward propagation to compute the gradients and update the model, right? And now, if we want to scale this training pattern, we face two problems. So first, what if the input data is very large? For example, we want to train on millions of images or millions of tokens, right? And second, what if the model or the layers are very large? For example, we want to train a model with billions of parameters like GPT-3. Okay, so the difficulty of these two problems are different. So the first problem is actually a lot easier and has been studied pretty well. It is called data parallelism. And I think you guys heard this term many times in these 2 days. Yeah, and we can partition the input data and replicate the model. So here are 2 GPUs. We can replicate the model on all GPUs, and then feed different input batches to different GPUs to parallelize this computation. And if you are a current Partition user or like PyTorch user, this pattern is actually addressed pretty well by all these existing libraries, like you can find on the open source, where you can find a ton of interface, like I showed in the previous, in the first part of the talk. And the second problem, however, is much harder. So if the model is very large, the size of the model can be much larger than the device memory and the device memory capacity. As shown in this figure, we need at least dozens of GPUs to hold the model, right? So we cannot afford to replicate this model anymore, like we did for data parallelism. So needless to say that we also have to store a lot of intermediate results. So we also have to partition the model. However, unlike the data set, which are just a sequence of files and usually are independent, the model is a complicated computational graph, and how to partition it is very, very non-trivial. Yeah. So now let's take a look at the computational graph and explain why it is so hard. So this graph begins with an input x, and we then have a lot of matrix multiplications, convolutions, and element-wise activations and reductions, this kind of mathematical operations. And this figures only shows the forward part of the graph, but the real graph will be more complicated with backward propagation and also the updating operation. So how can we partition the graph into 2 devices, device 1 and 2 here? So the most straightforward way is to cut the graph in the middle and put them on 2 devices. And this is called inter-operator parallelism, right? And the cut is actually not too bad because the communication across this cut is small. However, due to the data dependency, the second device cannot always be busy because it has to wait for the first device to generate its generate the output, and then the second device takes the output of the first device. So the second device will be idle at some time. And although this can be elevated by using pipelining, it still results in device idle time due to the dependency between forward propagation and backward propagation. Now, if we want all devices to always be busy, what should we do? So instead of partitioning at the graph level, we can partition each operator and let different devices work on different regions of the same operator, as this figure shows. So this is called intra-operator parallelism. And intraoperator parallelism makes all devices busy, but it leads to more frequent communication because devices have to sync after one operator if the next operator cannot preserve the previous partitioning pattern. So in summary, this page shows two basic patterns of how to perform model parallelism, how to partition graph. As I just mentioned, there are trade-offs between these two methods. So interoperator parallelism requires less communication, but has more device idle time. And intraoperator parallelism requires more communication, but the devices are always busy. So under this classification, there are more variants we can try to create. So first, for the intraoperator parallelism, there are multiple possible strategies to partition an operator. For example, for a matrix, we can partition it along rows or along the columns, or we can even replicate it on both devices, like we did for data parallelism. When connecting these nodes in a graph, so different partitioning strategies can lead to different communication and computational costs. And this is a very difficult combinatorial optimization problem. And for the interoperator parallelism, we can increase device utilization by pipelining the computation or multiple input batches. As shown in this figure, we can put 3 layers on 3 devices, and then we can keep all devices busy by letting them work on different input batches. So the intraoperator parallelism and interparallelism can also be combined, like that figure shows. We first cut the graph in the middle and into 2 parts for interoperator parallelism. And then for each subgraph, they do intraoperator parallelism inside this subgraph. So for a mixture of expert model, we can get the best performance only when we combine these 2 parallelisms as shown in this performance graph, right? Whereas the right is the combined one. So in summary, all these choices form a sophisticated space with many trade-offs. And given a model of interest, it's very hard to efficiently search for a good strategy in this space. And this is actually a hard engineering problem you are facing if you try to parallelize these big models. However, this is still not the tricky part. The next tricky part is how to map this partitioning to the actual devices you are trying to use to train or serve these models. So after partitioning the graph, we have to map the partitioning to the devices. So here is 1 GPU. It is definitely not enough for training large models. So I get a machine with 4 GPUs and more machines with more GPUs. And here comes the tricky part. So the network used to connect these machines shows a 2-level hierarchy. So where we have fast connections, we have fast connections for GPUs inside the node, as this green arrow shows. And we have slower connections across different nodes. So the challenge here is how to map the graph partitioning to this 2-level hierarchy so we can maximize the performance, right? So as you can see, this problem is very challenging and very important. In the past few years, people have developed various systems to solve the problems I just mentioned. I will list a few here. So each of the projects I'm going to show is developed by a good team of engineers and researchers. And each technique also typically enabled some breakthrough in machine learning side. Yeah. So to classify them, I draw 3 circles. So this red circle is the intraoperator parallelism I just introduced. And the yellow circle for interoperator parallelism. And this blue circle is whether the technique can be applied to an arbitrary model automatically. So first, people designed specialized strategies for specific models. Like NVIDIA's famous system, Megatron-AM, is a good example. And it designs a specific strategy for parallelizing the transformer language model like GPT-3. And later, they improve it by adding interoperator parallelism for better scalability. And there are also a lot of other systems trying to address this problem. However, they either cannot support both types of parallelism or cannot automatically apply to a customer model, meaning that they cannot generalize or they have very worse performance. And in contrast, Alpa is the first system that can solve both types of parallelisms automatically. So now I will spend a few minutes to tell you more about Alpa. So in Alpa project, our goal is to build a unified compiler that automatically finds and executes the best strategy with both inter and intraoperator parallelism for large deep learning models. So Alpa has a very simple user API. So Alpa provides a Python decorator at alpa.parallelize. And you can put this decorator on top of your Python deep learning training function, which is this train step function. And then the function is being called. When the function is being called for the first time, it will trigger compilation. And then the function will be parallelized and run distributed on your cluster. That's what happened. That's all you need to do in order to like play with big models using Alpa. And under the hood, this simple API is made possible by several innovations of the Alpa project. So to deal with the complicated search space I just explained, inter and intra, we organize them as a two-level hierarchical space. And then in Alpa, we designed many optimization algorithms to deliver, to derive the effective parallelism plans at each level with guarantees. And finally, we implement an efficient compiler system to generate the plan, parallel plan, and also a high-performance runtime to make sure that once the plan is generated, your training and the inference actually can run very fast on your cluster. So given an input computational graph, the entire model parallel strategy is a combination of OR, inter, and intraoperator parallel strategies. But we want to find the best performed one from this complex space. And the existing systems fail to do this because they do this by human experts or do this for a specific model. So in Alpa, the key to make this problem solvable automatically is to decouple and reorganize the search space. So more specifically, we first search for the interoperator parallel plan at the first level, and at the next level, we derive the best intraoperator parallel plan conditional on this interoperator parallel plan. So, and we design the Alpa compiler based on this search space decomposition, and the input of the compiler is a computational graph and a cluster specification. And we design 3 compiler passes to do this optimization. The interoperator pass finds the best interoperator parallel strategy with a dynamic programming algorithm. And the intraoperator pass finds the best intraoperator parallel strategy using an integer linear programming algorithm. And this optimization is also hierarchical, which means that the higher level pass will depend on the results of the lower level pass. And finally, the runtime orchestration pass will realize this parallel plan and actually execute that strategy and training. Cool. And I skip a lot of details about how Alpa is built, but you can feel free to check out the page. And that's a brief introduction about the technologies behind Alpa. But now let's move to talk about the use cases Alpa can provide now. In the current Alpa project, we offer 3 main use cases that are readily available: training, serve, and fine-tune, but all for big models. And existing systems or solutions cannot handle well because that difficult problem I just explained. On training, Alpa can train large models like GPT-3 with state-of-the-art performance. And on serving, Alpa can serve existing pre-trained models like Meta's OPT or the Bloom model. And on fine-tuning, Alpa provides a lot of flexibility, which means that by using Alpa, you will have more space to customize your model and model architecture, and Alpa will generate flexible parallel strategies for your specific model and cluster. Yeah, you don't have to like always pursue the best GPUs or best cluster available in the world. So we started developing Alpa from training large models. And so Alpa's single declarative interface is made very simple. And the backend is highly optimized on typical training workloads of big models, such as GPT-3, such as MOE, Mixture Expert by Google, and also such as some big computer vision models. And all you need to do is to append a single line of a decorator on top of your train step function. And Alpa will distribute the training on your cluster automatically with high performance. And I think in training, people care a lot about training performance, and people like to compare systems in terms of training performance. And we actually compared Alpa with previous works, like previous best systems in many different setups and models. And Alpa can guarantee a lot good performance compared to these existing systems. For example, in the first figure, you can see on GPT-3 model with up to 93 billion parameters, Alpa can match the best specialized many systems. And on the second model, which is the very famous Google's G-Chart MOE, Alpa is up to 10 times faster than Microsoft's DeepSpeed. And also on the third setup, which is a very big computer vision model, with no actually existing system can support it well. Alpa can generalize these models without like redo your entire system stack. And on serving, Alpa provides the first public unlimited free text generation for the OPT 175 billion. And you can try it immediately on that link. And here's a screenshot. And basically, you can type the prompts and on our serving cluster. On this web page, and our serving cluster will use several GPUs to run the inference. And we announced this service like 2 months ago to the public, and it actually becomes quite popular in the Bay Area. And on serving, Alpa has the 3 unique advantages under the hood. So first, Alpa serving is designed for serving large models like GPT-3, while most existing serving systems are limited to serve small models that must fit onto one single GPU. And second, Alpa can use a lot of commodity hardware to serve your big models, where many existing services, including those provided by cloud, they will ask you to rent A100 or V100, right? And third, since Alpa is a compiler, it also means that it's very, very flexible. So it will generate the optimal parallel strategy depending on your available hardware and your model, meaning that it can generalize to different types of models and clusters than existing systems. Okay, cool. And last, training a big model is very, very expensive, as Hector already mentioned. And it's estimated that training a big model can take like several $million. But this is not affordable for small companies or research groups. So fortunately, the community loves open science, and they make a lot of pre-trained models available to the public. And this page shows a few public available models like this Bloom, OPT, and also stable diffusion. And what I try to say in this slide is Alpa actually supports fine-tuning these models, all 3 models. And you can create your own data set and download the public weights and use Alpa to fine-tune these big models on your cluster. And hopefully you can also get very good results. Cool. And with that, I want to wrap up my talk with a quick summary. So I talked a bit the history about the parallel machine learning systems and how we get here with these model parallel systems and big models from a system perspective. And also, Alpa provides many use cases. I also talk about Alpa, and Alpa provides many use cases for big models. You can train, serve, and fine-tune big models on Alpa easily without worrying about how to parallelize them anymore, right? And you can focus on your machine learning development. And you can try Alpa immediately using our like free generating service. And please do not hesitate to start our project. And feel free to reach out to me after the talk, and I can provide you customer service. Yeah, cool.
All right. We have time for a few questions for Hao, so please don't hesitate if you want to know how this marvelously complex but historically very important piece of software is produced. Great. Okay. Yes, we'll just take a question behind you.
Hi, lovely talk, really enjoyed it. What I wanted to ask is, what I could gather is that Alpa generates or compiles a static graph, static computational graph. Does it mean that batch sizes of variable batch sizes are not supported?
For batch sizes, I don't think that's true, because in Alpa, what you can do is you can choose a few batch sizes and ask Alpa to compile different executables for different batch sizes. And the executable won't be very large because it's just several megabytes, and you can store that executable in memory. And whenever you want to use a different batch size, you just ask Alpa to choose that corresponding executable. Yeah.
So if we know the different kinds of shapes of the batches, it should be possible to train.
Yeah. Yeah.
So for an NLP application, that becomes very important.
Yeah.
Awesome.
Yeah. But extending your question a little bit, so if you have a very, very dynamic architecture in your model, besides batch size, like your model architecture will change with your training data, that will be something problematic in Alpa. Yeah. Okay.
Yeah, I could gather that because it's a static graph.
Yeah.
So is it only based on TensorFlow, or candidate?
It's based on a very generic compiler called SLA. I think someone yesterday introduced SLA. So SLA is a generic compiler that only serves as a backend, and it can support various frontend, including JAX, TensorFlow, and PyTorch. Yeah.
Awesome.
Yeah.
Cool. Great. Did we have another question? Okay.
Sorry, I was actually still a bit confused about the difference between 0 and what Alpa is doing. If you could elaborate a little.
Yeah, that's a good deep question. So I think the TLDR answer is 0 is a special case of an intra-operator parallelism I just introduced. Yeah, but Alpa covers a much larger parallel space, including intra and inter. Why we need to cover that? Because for some models, if you don't do inter, you won't get performance. Yeah. Okay.
There's one question online.
There's a question online.
Thank you. There's one question online from Maxime. What is the current state of development of Alpa? Is it plug and play?
Yes. For the use case I just presented, yes. But we are extending Alpa to more use cases like fine-tuning stable diffusion or serve multiple models simultaneously like that. Yeah.
Great. Any remaining questions from the audience in this room? Right. In that case, let us thank our speaker once more.